Okay, here's your optic chiasm. And here's your optic tract. Okay, does anybody remember the name of the nucleus? Yeah, lateral geniculate nucleus of the thalamus. Great. Okay, so we're pretty close to what we just drew, or what we just talked about. This is going to be a little bit different. Okay, is everybody caught up? Is everybody any questions about what you see? So all I've done is this is that same section that I was looking for, the transverse section through the eyeballs, looking at the optic nerve, chiasm, and tract, connecting to the lateral geniculate nucleus, and this is also another transverse section through the midbrain. Okay, and then if we move up here, what I'm showing you, these are eyes. Okay, this is the right eye, and this is the left eye, and we're going to do something called the pupillary light reflex. We're going to look at the pupillary light reflex. Other players. So we also have to draw in that cranial nerve nucleus that's involved in pupillary constriction. Does anybody remember what that one was? Yep, that's your Edinger-Westphal. So your Edinger-Westphal nucleus is going to be, we'll draw it right in here. Edinger-Westphal. And oftentimes I've been talking about something known as the superior colliculus, where the third cranial nerve, the nucleus is located at the level of the superior colliculus, and that's these two little bumps, and those are that two little bumps that I've been talking about. One important thing to know that resides in the area of the superior colliculus is something known as the pretectal area. So two little nuclei here, and this is called the pretectal region or pretectal area. Pretectal region or area. Your pretectal. Okay. And when you do the pupillary light reflex, you're going to learn how to do it next year in our rehab. But you typically do this, and you're going to perform it in a dim room. So if you're in a dim room, the pupils of your eyes are going to be great big and dilated. Okay, so this is how you start. Start the test in a dimly lit room. Pupils are great big and dilated. And what you're going to do is you're going to shine a flashlight into one of the eyes. Let's just say here, let's say this is the right side, and this is the left side. So you're going to shine the flashlight here into the right eye. This is my little rendition of a flashlight. Okay, there's a flashlight that's shown just into the right eye. Okay, what would be the response of the right and left eyes after you shine? What's the response to the pupils for the right and left eyes? Does anyone know? Yeah, they both constrict. So even though you only shone the flashlight into the right eye, both pupils constrict. The right pupil constriction is known as the direct response. It's a direct response to receiving light in that eye. Okay, and then you also know that the left pupil constricts as well, and this is called the consensual response. So there's a direct response and a consensual response. The direct response happens in the same eye, and the consensual response happens in the opposite eye. Even though that left eye didn't see the flashlight directly, it still caused pupillary constriction. Okay, questions about that? And this pathway is just going to show you how that happens. Okay, so what I'm going to do is down here I'm going to have the flashlight shown in my right eye. Okay, so I'm shining a flashlight in somebody's eye, and what happens is that light is perceived by both the nasal and temporal retina of the right eye. And what we've seen is that the temporal retina for the right eye just comes right on down and stays ipsilateral and synapses with the lateral geniculate nucleus on the ipsilateral side. And that the nasal retina that travels down the optic nerve goes contralateral side through the optic chiasm, travels down through the optic tract to synapse with the lateral geniculate nucleus on the left side. Okay. So nothing new so far. What you haven't seen yet is that there are some axons that actually don't synapse here in the thalamus or the lateral geniculate nucleus. There are some axons that come through the optic tract and end up synapsing here in the pretectal region ipsilaterally on both sides. So they don't synapse. There's some axons that come down and they just synapse here in the pretectal region. And then the pretectal region sends out axons that synapse with the ipsilateral Edinger-Westphal nucleus and the contralateral Edinger-Westphal nucleus. And the axons from the left pretectal region synapse with the ipsilateral Edinger-Westphal nucleus and the contralateral Edinger-Westphal nucleus. Edinger-Westphal nucleus travels as part of cranial nerve number 3. If you remember, axons from the Edinger-Westphal nucleus traveling as part of cranial nerve number 3 come on up here and synapse with the ciliary body and the sphincter pupillae. Bilaterally. Okay, and that's how you get pupillary constriction of both eyes. Question, Alex?
Yeah, is it like I forget when we like learned this, but it didn't synapse in the pretectal region. Like, are people still constrict since it's still going to the lateral geniculate sphincter?
So no, this doesn't have anything to do with pupillary constriction. This just has to do with vision. Okay, the pupillary constriction has to do with making it all the way down to the level of the Edinger-Westphal nucleus, because the Edinger-Westphal nucleus is the one that's responsible for the pupillary constriction through cranial nerve number 3. Okay, so does that make sense? Other questions? So shining light into the right eye ends up with synapses to both lateral geniculate nucleus bilaterally, as well as some axons traveling down through the optic tract synapse with the pretectal region. Okay, the pretectal region sends out axons that synapse both ipsa and contralaterally with the Edinger-Westphal nucleus, and since both have been stimulated, you get pupillary constriction bilaterally. Okay, let's move on. Last one. The pupillary light reflex. Clinical implications. Okay. So, keep that handy. Again, we're just going to take these one at a time. Okay, when you do the pupillary light reflex, you always shine the flashlight in both eyes. Okay, so let's just start out here. You start out doing the test in dim light. In the first situation, we're going to look at a left cranial nerve 2 defect. That means the problem is right here. Okay, this part of the cranial nerve. So if I have a left cranial nerve 2 defect, we're going to look to see what happens when we shine the flashlight in both the right and the left eyes. Okay. To start the test, you're in dim light. So both the right and the left pupils are going to be great big around. Okay, and we're going to start out by shining the flashlight in the right eye. Okay, if you're working with somebody with a left cranial nerve 2 defect, and I shine the flashlight in the right eye, what happens to the size of the pupils? So the right constricts, but the left doesn't. So the right constricts. Okay, but let's look at that. So if I have a left cranial nerve 2 defect, the defect is here. Okay. Sorry? Both still constrict. Yes. Does everybody see that? So if the defect is here, there's no problem with the cranial nerve 3 pathway. It's just cranial nerve 2 on the left side is broken. That means light comes in the right and does everything it's supposed to. Does everybody see that? I see one head. Yes, Johnny?
Cranial nerve 3 factor in? Sorry, I missed it.
That's okay. Cranial nerve 3 is here. It travels as part, remember the Edinger-Westphal nucleus sends out axons that travel as cranial nerve 3.
So the final synapse is
This.
cranial nerve 3 route?
So when the axons come out of the Edinger-Westphal nucleus, they travel as part of cranial nerve 3. So this is cranial nerve 3. Does that help? Okay, so can everybody see that if I have a left cranial nerve 2 defect, I shouldn't get any change in pupillary constriction in either the right or the left eye? Okay, so both the right and the left pupil constrict, because pupillary constriction is all about cranial nerve 3. And like I said, we have to do the test. To do the test, you have to shine the flashlight in both eyes. So to start the test, pupils are great big around. And now this time I shine the flashlight in the left eye. What should happen? So here's my defect. Oops. My defect's right here, and this time I'm shining the flashlight in this eye. What would I expect to see as far as pupillary constriction? Anybody?
No change.
No change. No change in pupillary constriction. Okay, I'm going to have great big old pupils. And the reason is because there's no light getting into the system. Okay, so if no light gets in because my defect is right here, I don't see any change. Does that make sense? I'm waiting. No, not yet. Okay. Okay. How about another way to think about it is what happens if I have a defect, a right cranial nerve 2 defect, since I've drawn it out on the right side. My defect is right there. So nothing gets past where that marker is on the right side. This time I have a right cranial nerve 2 defect, and I'm shining the flashlight in the right eye. What would I expect to see? Okay, Sydney's got it.
No change then?
No change, because no light's getting into the system. Nothing goes past the marker. It's cut off from here. Okay. In order for the system to work, I've got to get some light into the system. Does that help, Johnny? Okay. All right. So no change with a left cranial nerve defect. I don't have any pupillary changes whatsoever because no light's getting into the system to stimulate the light reflex. Okay, so cranial nerve 2 is the afferent part of the reflex. Cranial nerve 3 is the efferent part of the reflex. Does that make sense? Cranial nerve 2 detects the light, afferent information coming into the system. Cranial nerve 3 puts out the parasympathetic motor activity, the efferent limb of the system. There are neurons firing. I can hear them. All right, let's look at a left cranial nerve 3 defect. Okay, that's going to be down here. We have, to start the test, I'm going to start out with pupils that are great, big, and round, all dilated. And I'm going to start by shining the flashlight in the right eye. But here, this time, I'm looking at a left cranial nerve 3 defect. That means if I look at this picture again, my defect's going to be here. I'm going to knock out this third cranial nerve coming out of Edinger-Westphal. So shining the flashlight in the right eye, light gets into the system, travels down to the level of the Edinger-Westphal nucleus, but my third cranial nerve isn't working here on the left side. So what would I expect to see?
Only the right side.
Yep. Only the right side has pupillary constriction. Great. So I see pupillary constriction on the right, but I don't see any constriction on the left because the nerve that's responsible for that constriction isn't working on that side. The nerve that's responsible for the efferent limb of the system is blown on the left side. Hence the blown. Alex, that you asked about before. This is a blown pupil. Can't respond to light. Okay? And the same thing, left cranial nerve defect. Remember, you got to shine the flashlight in both eyes. If I shine the flashlight in the left eye, what would I expect to see? Going back to the picture, so what I'm doing is I'm shining my flashlight in this eye, and this is still broken.
Just the right side?
Just the right side. Correct. Does everybody see that? Because light gets into the system, reaches the level of the Edinger-Westphal nucleus. Again, the left is still broken, but the right can still respond. That's the consensual response for the right side. So I get a left cranial nerve 3 defect. I shine the flashlight in the left eye. I get constriction of the right pupil, but I don't see any change in the left pupil because that third cranial nerve is not functional on that side. This is the consensual response. So the light's getting into the system, and the right is constricting because that's the consensual response. In this case, this constriction would be the direct response, and this would be the consensual. Questions? Okay, let's go ahead.